One of the challenges in this chapter on vector calculus is keeping all the various theorems straight and the situations straight. And so here at the end of the section on Green's theorem, there's a nice review in the text. And I thought I would take a few minutes to just kind of walk through some of the high points of that review table. So table 17.1 shows the parallel properties of conservative and source-free vector fields in 2 dimensions. And so we're going to assume that C is a simple, piecewise smooth, oriented curve and is either closed or has endpoints A, B.
Time now for the weather, and Rob Marciano is up.
Nice. So on the left, we have a section on conservative fields. So conservative fields, remember, these are ones where a conservative field is a field that has a potential function. So they have a potential function phi where f, the field, is equal to the gradient of phi. So if you will, these are gradient fields. Gradient fields. So here we have the 2D version of curl. So here, this is the 2D version of curl. And our first statement is that the curl is equal to 0 if we have a gradient field. The potential function can be found in as follows, where f is equal to the partial derivative of the potential function with respect to x, g is the partial derivative of the potential function with respect to y. And so we can do our anti-differentiation process that we talked about earlier. Talk about circulation. Remember, circulation is the work to go around a closed path. And so the circulation would be the work to go around the closed path. And since it's a conservative field, there would be no work done. And then to evaluate the line integral, we have this nice theorem, our fundamental theorem of line integrals. Line integrals. And so the fundamental theorem of line integrals says that you can evaluate the total work done by simply finding the difference in the potential from the final potential minus the initial potential, and that will give you the total work done. That's for conservative fields. So for source-free fields, these would be places where the divergence is equal to 0. And again, this is the 2D divergence. We'll talk about divergence later with 3D. So in source-free fields where the divergence is 0, we have this new function, psi, which is our stream function. And so the components f here would be the partial derivative of psi with respect to y, and g would be the partial derivative of psi with respect to x, but now negated. And this kind of gives us the green theorem in a different form. So flux, this is one of our new quantities. Flux is equal to now the normal component of the force. Back here we had F dot T. So with work, we were looking at the tangential component. With flux, we're looking at the normal component on all closed curves. And to evaluate the line integral, again, the normal component, or the flux, we would use that fundamental theorem of line integrals, and we could evaluate the difference of the psi function from the end to the beginning. With Green's theorem in the picture, we may also give a concise summary of the various cases that arise with line integrals of both circulation and flux. And so this is in the next table. So notice that if things are closed and conservative, then the work done is 0. That's nice. If it's not closed, then we use our fundamental theorem of line integrals. And specifically, remember, we're here working up with circulation / work integrals. So F dot T, this is the tangential component of the force, or F dot R, or F dx plus G dy. If F is not conservative, then, and things are closed, then we definitely recommend using Green's theorem. It's really nice. Or you can do direct evaluation. In this case, you're going to have to parameterize. In terms of order of difficulty, this is the easiest because the answer is just 0. This is the hardest right here. And then if it's not closed, here you've got to find the potential function most often. And if we're in this bottom case with Green's theorem, you have your choice of evaluating things using the parameterization, evaluating it directly, or if you want, you can use the double integral, either or. So this is the Green's theorem category is the nicest one in the sense that you actually have a choice of how to approach it, whereas in the other places you don't have quite as much of a choice. All that is for finding circulation or work integrals. If we want to do the parallel analysis, but now talking about flux integrals, remember the flux is talking about how much stuff is going through it's going through the curve. That is, we're trying to find the amount of the field that is normal to the curve. We could calculate that directly using the formula. The flux is equal to F dy minus G dx. Notice this is the y component here and the x component there. So if our field is source free, this would be where the divergence is equal to 0. Then we have that if the loop is closed, that the total of the normal component would be 0. Yay. If it's not closed, then the total of that normal component would be the difference in the potential function, that psi potential function. So find the potential at the endpoint minus the potential at the initial point. Difference would be the total flux. If F is not source free, notice the parallel. This one is paralleling the idea of F being not conservative. Then you have your choice with Green's theorem. Here again, we could calculate it directly, or we could use Green's theorem and change it over for a double integral. In this case, notice you have the sum of the two partial derivatives, whereas above you had a difference, and the orders are reversed. So you have, again, with Green's theorem, you have a choice of how to go about things, which is nice. And then kind of our hardest option is always to do things directly. And so our hardest option, we could find the flux or the normal component of the field by evaluating F and then dy minus G dx. Notice that here at the bottom, the first step will again be to parameterize. Just for clarity's sake, I want to make sure it's clear. You could parameterize instead of using the fundamental theorem of line integrals. You could parameterize instead of taking advantage of the fact that the flux is 0 around the closed path. You could parameterize instead of using Green's theorem. But it's only in this last case where C is not closed and F is not source free that you're forced to parameterize. You don't have the choice. Similarly, up above, you could parameterize in all these cases. You could parameterize instead of using the fundamental theorem of line integrals. You could parameterize instead of taking advantage of the fact that the work is 0 around a closed path of a conservative field. You could parameterize instead of using Green's theorem. But it's only in the case where C is not closed and F is not conservative that you must parameterize if you're going to calculate the work. And so since generally speaking parameterization is challenging, we try to take these other approaches if and when it's possible to save ourselves a little bit of pain and anguish. So I hope that helps by way of a review of what's going on in this section, understanding both how the tangential component of force along a curve gives you the work, the normal component gives you the flux, and the good things that happen to work when you're dealing with a conservative field, the good things that happen to flux when you're dealing with a source-free field. Take care.